of the porous rotor technology. What porous rotor technology is what we do is we replace the standard rotor, which is a bladed rotor, with a foam ring. What the blades do is, as they come around, they push the air onto the forward surface of the blade, creating a higher pressure along that forward side of the blade. On the back end, on the trailing edge of the blade, what they do is they create a lower pressure. At the exit point of that rotor, right at that leading edge of the rotor blade, what will happen is that the two air streams will come together and basically slap together, generating noise. That's the reason why standard hair dryers are very noisy. For us, first off, we don't have that slapping of the air, since there's a nice, smooth, gradual transition of pressure from the inner surface of this ring to the outer surface. The air, as it's being spun around through centrifugal force, wants to exit, and that's what gives us this type of a flow. So what we end up with is a nice, smooth pressure transition going from the inside surface of this ring to the outside surface, and you don't have that air slapping against itself. Also, because we do grab the air so much more than we do is done with bladed rotors, we run at a much lower RPM, and the frequency of the sound is greatly dependent on the speed of the rotor. So what you'll hear is that not only is the sound level lower, but also the type of sound that's generated is of a much lower frequency and much more pleasant. What I have here is a standard Conair hairdryer. It's called the Euro 16 Turbo type hairdryer, and this is our prototype. This was made in Hong Kong, and basically what we have is at the settings that I have these both on, I'll be running them both on high, and they're both running at the same air volume, which you'll see in a moment. You can hear the high-pitched whine of this technology. And here is a much lower frequency, not so bothersome. Keep in mind, these are both generating the same amount of airflow. What I've just shown you was our latest prototype, but that's not the way that we started. Our first prototype utilized a foam ring, as you can see right here. Well, I'll show you a close-up of it. The prototype that you've seen just previously, our latest one, has an inside ring of fan blades that help to make the technology a little bit more efficient. This hairdryer prototype is basically is our quietest unit that we've ever built, but there are some trade-offs that aren't really acceptable for production. One of them being is we use a special type of motor, which is what they call a cupcake or muffin type motor, and although it's very quiet, very smooth running, it's also very heavy and expensive, so it prohibits us from using it in our application. The standard motor, or the type of motor that is used in hairdryers, is a DC brush type motor. What we've done is in the prototype that you have seen, we use a very high quality and also a one that has 5 poles, which makes the running of it a lot more smooth. All DC motors have a little bit of a jerkiness in them when they rotate, so that adds to the sound levels produced, the pulsating type of sound. Turn this on. As you can hear, it's quite quiet. This is running at about what a standard hairdryer would be at, about on low speed. We have some other prototypes. One of the other things that we did was that we took standard hairdryers and just modified the insides of them so that you could make a comparison of the two types of technologies. We left everything the same on these two hairdryers, with the exception of the rotor. So the heating element and the motor and all that, and the air passages and everything are the same on these two units. What I have is them set on so that they're both running at the same airflow, and you can hear the difference in the two. This is a standard hairdryer, and here's a hairdryer using the porous rotor technology. Again, what you can hear is a difference not only in sound levels but also in pitch. This is a close-up of the foam rotor. As you can see, when we take it and hold it up to the light, you can see right through it. This graph is a comparison of the standard unit and the two other prototypes that we built originally. This is the Vidal 1500 that we were talking about, the Quiet 1500. And that goes to this line on the graph. This is our modified unit where we replaced the standard bladed rotor with our foam rotor. And that relates to this line on the graph. And then we have our first unit that we put together with the foam rotor and that special motor that I spoke about. And that's these two lines. You can see here what the difference is between these two units, and that's the difference being that we remove the heating element in the two. So you can see the large source of noise does come from the heating element, and that's why we spent so much time developing the unit, the heating unit that we have in our current production prototype. What this graph is telling us is that we've made a great reduction in sound levels in between the standard unit and then the modified one. You can see about a 10 dB decrease in sound levels, which is dramatic. What you're looking at is a device that I use to compare airflows of various hair dryers. What we have is a tube that the inlet right over here is where I'll be placing the hair dryers, and at the other end here what we have is a propeller type anemometer, wind anemometer. I'll give a little blow down the tube here. And you can see the propeller run, and you can see that we're getting a measurement down at the bottom. Here you can see the Conair unit. I have it on high speed. Let's see if we can get a number on here, as you can see. Rating at 7.6, 7.7 about. Conair unit that high. And here you can see our unit. Running about 7.7, 7.8. What we have here is a dB meter. It's measuring the A scale, and although this isn't exactly the right way to do this test, you can at least get a comparison. What we have here is a line that's 3 feet long, and it's going down to the bottom of the unit. You can see. Normally you won't have all these surfaces around, and if we take a look at the sound levels here, they're a little bit below 40. If I start talking, we're up at around, what is that, 60. So you get a rough idea of what sound levels are. Okay, let's try it. Okay, and we're measuring. Looks to be just about 58. Okay, here again we have our meter. Again, we're about 3 feet away, and as I had said also, this is not the proper way to do this test, but for comparison purposes it's okay. Turn her on, put her on high. You see there we're about 74. The device that you're looking at is a spectrum analyzer. What it does is it breaks down sound levels at different frequencies. If we turn it on, you can see by my voice, maybe you can't see by my voice, there we go, what the various levels are at the different frequencies. This is used for us to be able to see where the peaks are with the various hair dryers that we've got, or the two I should say. Here we go, here's the Conair. See, that's somewhere around the 2 to 4 peak. And it's peaking around 4 kilohertz. And here we go with the porous rotor fan. As you can see and hear, that's at a much lower frequency. So the combination of the lower frequency and also the just decrease in overall sound levels, it's a much more pleasant sound that it emits. This is a standard hair dryer, a Conair turbo hair dryer, 1500 watts. And you can hear the sound that it's generating. This is in a fairly closed area, normal bathroom sort of environment with hard surface walls. And you can hear the difference between that high-pitched whine and our porous rotor type hair dryer. Not only is it a lot quieter, but the type of sound that it generates is a lower frequency, and it doesn't travel so well. As you can see, I'll walk through the door, close it, and you can barely hear it. Standing about 5 feet away from, or actually about 8 feet away from the door. Now we're switching over to the other type of hair dryer. You can hear it. The high-pitched whine. Thank you for watching this presentation. Hopefully you've been able to get a good feel for what the porous rotor technology can do and its relative merits, both in overall sound level reductions and as well as lowering the frequency of its noise. The technology is covered by 3 issued U.S. patents, and we also have 1 patent pending in Europe. The unit that you saw was designed both with my group, basically myself, and Jim Montagnino. Jim Montagnino is was a past head of engineering, vice president of engineering at Helen of Troy, which is the manufacturer of Vidal Sassoon products. Also, we spent many years at Clairol. We have a complete drawing package, and we're basically set to go. We have a factory in Hong Kong that's ready to go, and with tooling and everything and some modifications that we'd like to do. We're looking at about 6 months from the start date till the time that we can have product ready for shipment over to here from Hong Kong. Well, I hope you've enjoyed this presentation, and if you have any questions, please feel free to contact me, Karsten Idland.